Welcome, ladies and gentlemen. My name is Hubertus Böhm. I'm a process automation specialist with focus on oil and gas, including hydrogen industries. I will show you some application examples within the hydrogen value chain, where Siemens has contributed as partner to successful process implementations. The need to reduce carbon dioxide emissions drastically has brought hydrogen to center stage to decarbonize entire industries. Hydrogen is not new at all. Already today, the global annual demand is 80 million tons. It is mainly consumed in refineries and ammonia plants as feedstock for fertilizers. So what is the value chain? I would like to focus on the evolving applications in the center of the picture that include the green production methods of electrolysis or also methane pyrolysis. Storage and distribution is a big challenge. Conventional methods like compression and liquefaction consume lots of additional energy and require expensive infrastructure. New methods include LOHC, or chemical conversions referred to as power to liquid. In this context, carbon capture and usage plays an increasingly important role. Aviation, for example, and air traffic will depend on liquid fuels and have started with on-site production on their way to become carbon neutral. Here is a more detailed overview of the hydrogen value chain, grouped into three categories: production, storage, transportation, and usage. On the top, we see the conventional large-scale productions based on steam methane reforming or coal gasification, and they are around for long. Unfortunately, these processes release significant amounts of carbon dioxide, so that we call them gray. The new technologies around production of green hydrogen are typically modular plants and produced by package unit builders. We see new applications around storage and transportation, such as liquid organic hydrogen carrier or ammonia crackers. Siemens has helped startups to move from laboratory scale up to industrial production. Electrolyzer and fuel cell production is a separate topic. Let's take a closer look at the electrolyzer system. An electrolyzer system consists of several package units. The core is, of course, the electrolyzer itself. To make it work, we first need a power supply of typically 2 to 3 megawatt electric power, direct current. Then we need lots of water. 10 tons of water are used to produce 1 ton of hydrogen. And it's not just water, we need demineralized water. An ion exchange unit controlled by a cymatic PLC is good enough for use with fresh water. Seawater would need a full-fledged reverse osmosis plant. The example shown here is from Stadtwerke Mainz. The installation features 3-unit Siemens 200 powered by 4 windmills nearby. Stadtwerke Mainz operates a filling station for bottled hydrogen moved by trucks. They also feed hydrogen into the natural gas grid. This is then used for residential heating. Let's take a closer look at the different package units. The transformer rectifier unit is quite space-consuming. They are either air-cooled or water-cooled. Siemens is using air-cooled Dynamics DCM rectifier units. For water-cooled rectifiers, Dynamics DCM control unit is managing the fluctuating electric power supplied by windmills or solar panels. Siemens offers design, engineering, and installation supervision. The core component of an electrolyzer system has about 40 measuring points for temperature, level, pressure, and flow. Most of them need to fulfill ATEX requirements for Zone 1 or 2, as well as Safety Integrity Level 3. Siemens can provide products with the required ratings. Hydrogen is also very demanding when it comes to sealings. It is so small that it is leaking through materials that are otherwise gas-proof. Gold plating of diaphragmas may be required at higher temperatures to avoid hydrogen corrosion. This happens when hydrogen connects with the carbon molecules bound in steel. Siemens has the right products. Needless to say that for alkali electrolyzers, the instruments withstand the aggressive alkali lye. Hydrogen users, specifically the mobility sector, for hydrogen use in fuel cell vehicles has demanding purity standards. They are specified in European norm 17124 and in ISO FDIS 14687. This is important to increase the lifetime of the membranes of fuel cells to reasonable levels expected by users of fuel cell vehicles. And purity is key. Our Maxim chromatographs are well proven in hydrogen productions that use methane or natural gas as feedstock because they bring other pollutants to the process that can be detected. For electrolyzers, it is usually sufficient to monitor the hydrogen and oxygen molecules that come out on the wrong side. For oxygen and hydrogen, oximat is used. Hydrogen and oxygen, it is detected by calomat. All package units have to be orchestrated by an overarching control system. Simatic PC7 is used here in a power-to-gas plant located in Grenzach-Wielen, close to the Swiss border. The electrolyzer used here is one based on alkali lye. It is the most robust and long-living technology on the market. The downside is it takes almost 3 hours to start it up. Speed is where proton exchange membranes electrolyzers have advantages. But this one here is powered by hydropower from the adjacent River Rhine. That is a constant and reliable energy source. Modular automation solutions support scaling up by numbering up. OEMs can secure that intellectual properties within their own package unit to protect their process know-how. Looking at membranes, or more precisely, the membrane electrode assemblies, MEA. There is one in each cell. Up to 250 cells form a stack, and a Siemens 300 has then up to 24 stacks. The process of coating electrodes on each side of the membrane is the intellectual property of the MEA producers, and that is kept top secret. The software GPROMS from PSE, a Siemens company, is helping fuel cell producers to optimize the design of the fuel cell. The goal is to convert the hydrogen completely on its way through the stack, while minimizing its footprint and usage of electrode materials such as platinum and iridium. The software models a digital twin and is capable of simulating chemical reactions on the diffusion layer and helps the developer to avoid frequent prototyping. Another application within the hydrogen value chain is the refueling station. A known supplier for technical gases in southern Germany is also a frontrunner for building hydrogen fueling stations. Siemens did not only provide process instrumentation and control equipment, but also a special outdoor panel from the Simatic HMI offering. It copes with a wide temperature range and offers good contrast on the display even when exposed to the sunshine. We also co-created a MindSphere application that helps them to monitor critical process parameters remotely. Information is transmitted securely by our IoT gateway IoT 2040. Another iconic reference is the multi-energy fueling station at the new Berlin airport. It is owned and operated by Total. McPhee not only supplied the electrolyzer, but also acted as EPC. Simatic PC7 orchestrates all package units, including the electrolyzer. The installation also features re-electrification by 2G Energy. It is a combined heat and power plant powered by hydrogen. One more example addressing the storage challenge: liquefied organic hydrogen carrier, LOHC. This is one example where Siemens has not only helped a startup to scaling up from laboratory scale to industry level, but also to expand their business overseas. LOHC is an oil already known from heat transfer applications. It has the capability to solve hydrogen, much like coffee does with sugar. The energy density is about a quarter of the same amount of diesel. The oil is not consumed, it only releases the hydrogen by adding heat, and can be charged again and again. The charging process is exothermal, which mandates safety integrity level 3. Last but not least, there is e-fuels as important application. Siemens is also engaged in university projects such as Copernicus, driven by the Karlsruhe Institute of Technology. Simatic S7 1500 with TIA portal controls the Fischer-Tropsch reactor by Ineratec. I close with a summary. Hydrogen will play a key role to decarbonize the transportation, energy, and industry sector with modular plants. Modular plants allow scaling up by numbering up. Siemens' automation portfolio perfectly supports such architectures. Industry customers enjoy process simulation and cloud-based applications for improved operations performance. And package unit builders and EPCs are finding in Siemens a strong partner for electrification, automation analytics, and digitalization. Siemens' digital industry portfolio, application know-how, and project references are well suited to help you to grow in this emerging sector. These were only a few applications from the larger hydrogen value chain. I hope I could give you some inspiring aspects. Thanks for watching, stay healthy, and have a nice day.